Hi, this is Alex from devstories.eu. Mastering DeepChem, episode 15 of 15. You want to design a highly stable molecule, but you do not have a massive dataset of perfect examples to train a model. You just have a set of physical rules. When you lack static data, you cannot use standard supervised learning. Instead, you need an AI that learns by trial, error, and feedback. That brings us to reinforcement learning in science. If you are steeped in traditional machine learning, you might confuse this with supervised training. They are fundamentally different. Supervised learning requires an explicit, labeled static dataset. Reinforcement learning relies on continuous, interactive rewards generated by an environment. The model tries a move, the environment responds with a score, and the model adjusts its strategy. In DeepChem, the foundation for this interaction is the environment class. Think of the environment as your high-fidelity scientific simulator. It defines the physical rules of the universe your AI operates in. It tracks the current state of your system, defines the mathematical actions your model is allowed to take, and exposes a step function. When your model takes an action, it passes it to that step function. The environment calculates the physics, then returns three things: the new state, a numerical reward based on how good the resulting state is, and a Boolean flag indicating if the task is finished. If you are already working with standard tools from outside chemistry, DeepChem provides the GIM environment class. This simply wraps standard OpenAI GIM simulation environments so they plug directly into your DeepChem workflows. The component that actually interacts with this environment is called the policy. The policy is the abstraction representing your agent's brain. It takes the current state from the environment and maps it to a specific action, or outputs a set of probabilities for different possible actions. To train a policy efficiently, DeepChem implements algorithms like Advantage Actor-Critic, usually referred to as A2C. Here is the key insight. A2C splits the learning process into two separate neural networks running in parallel, the actor and the critic. The actor looks at the state and decides what action to take to progress the task. The critic watches the result and estimates the overall value of being in that new state. The word advantage refers to the difference between the actual reward received from the environment and the reward the critic predicted. If the action resulted in a higher reward than the critic expected, the advantage is positive, and the actor network is updated to take that action more often in the future. Consider a concrete scenario where you want to autonomously construct novel molecules. Your environment is a chemistry engine programmed to calculate molecular stability. You start with a basic chemical ring. The actor evaluates this starting state and decides to attach a carbon atom. The environment processes this step, simulates the new chemical structure, discovers a drop in stability, and returns a negative reward. The critic observes this outcome, updates its baseline expectation, and signals the actor that this was a poor move. In the next iteration, the actor tries attaching an oxygen atom instead. The environment simulates the change, calculates higher stability, returns a positive reward, and the critic reinforces that choice. Step by step, the A2C algorithm navigates the chemical simulator, building a complex, highly stable molecule entirely autonomously without ever referencing a static dataset of good molecules. Reinforcement learning agents can query simulators millions of times, discovering solutions human intuition might completely miss. This episode brings us to the end of our deep dive into DeepChem. If you want to take these tools further, explore the official documentation and try building your own environments hands-on. You can also visit devstories.eu to suggest topics for future series. That's all for this one. Thanks for listening, and keep building.